Hi, this is ET250 Lecture 24 Part B, the second part of the last lecture. And what we're going to look at is just a power factor correction example. We saw this before, but I just wanted to do a little deep dive onto it and then show you how do you calculate a C that'll correct the power factor. Now, here's a situation where you have like a factory, a power plant, this is like PG&E, and you have some current, some transmission line current that goes from the power plant to the factory. Now, usually this load will represent as a simple load your entire factory. It consists of motors, so it's inductive. So you usually have a lagging power factor where this current lags that voltage, okay? And this results in a positive Q, and the power, that means that the power bounces back and forth, or there's a component of power that bounces back and forth, right? And so that means the overall current is larger than it needs to be. Okay, and so that means the S, the apparent power, the hypotenuse of the power triangle gets larger, right? We want to still get the same amount of real power, average power out without having to have too much bounce back and forth, all right? Now, by adding a capacitor, we're able to do that. We've seen this before in a previous lecture, and we can bring that power factor closer to 1, which means that if we have a constant voltage, I is going to be smaller in amplitude, and the S will shift closer to the x-axis on the complex plane. Okay, and this will reduce the line currents and we can use more of the apparent power. These are all good things. That is the intention. And why do we like that? Because PG&E has less line currents, less wear and tear on their lines, and they incentivize us as the factories to do that by charging us a cheaper rate structure by having a closer unity power factor. So let's look at this example where we actually throw some numbers at it. So again, we have like PG&E utility, and we have our factory designated by a resistor inductor. This will be ZL. We have the I, and then let's say we're operating at 60 hertz. So that's corresponding to 377 radians per second. And we have 10 kilovolts RMS, and let's say this is 720 ohms and 2.546 henries. All right. And so the question asks, why don't we compute, before we put the power factor correction capacitor, what is the P, what is the Q, what is the power factor in theta V minus theta I, and the S for just this load, and then plot the complex power S bar. Okay, then let's compute the C needed to be put in parallel with ZL such that the power factor is now 0.9 lagging, so pretty close to 1. Now the thing is, if I had a capacitor here in parallel, this P should remain constant for ZL because the voltage here is not changing. So C just adds reactive power. Not only does it add reactive, it adds negative reactive. So it's canceling out this positive reactive power here. So this is what it should look like when we add that new capacitor. All right. So if we just look at the resistor and inductor by itself, what do we have? Well, we have R plus J omega L. We just did that in the last lecture. And we know our equation for real power. If we just know the voltage and the resistance is this, VRMS squared, real part of ZL, which in this case is R, not always true if it's in parallel, over the magnitude of Z squared, which is just the Pythagorean theorem of that. Okay, good. So this is 10K squared times R over square root of R squared plus omega L squared, no problem. And we can actually calculate a number. Notice the square root and the square cancel here, right? You see that sneaky little square and the square root, they cancel. Don't forget that. I forgot that when I was doing this example. So don't forget that, and we get power equals 50 kilowatts. Okay, so the real power for the ZL is 50 kilowatts. Now, if we want to calculate the reactive power, right? And remember, what is real power? It's the average of the instantaneous power. What is reactive power? Is the amplitude of the component of the instantaneous power that bounces back and forth. Good. So VRMS squared times the imaginary part of ZL over the magnitude of Z squared. I only switch the R for IM, good, or the real for imaginary. And I pretty much take the omega L part here instead of the R part. Otherwise, the denominator is the same. It's just R squared plus omega L squared because the square and the square root cancel. So this is the number I get when I punch everything in. You could pull out your calculator and test this, and you get 66.67 kilovars. All right, kilowatts, kilovars. Okay, so by complex Ohm's law, right, we can look at the phase of this total voltage and current, right, the phase difference, right? So how do we do that? Well, we already did this in the last lecture, right? The phase is omega L over R, good. And so that's equal to theta V minus theta I. Okay, what do we get here? We get 377 times 2.54 over 720. So we get a 53.13 degree phase difference between the voltage and current where the current is lagging. What's the power factor? Okay, so these are all questions I'm just knocking down. Power factor is just cosine of theta v minus theta I. So cosine of that number ends up being 0.6. So 0.6, that's not a great power factor. Notice we want 0.9, but we have 0.6 at this certain point. So we can add that capacitor and that'll definitely help us. What is the S? Well, we can use the Pythagorean theorem, p squared plus q squared square root, and that's the magnitude. So that ends up being 83.3 kilovolt amps. And what do we have here? We have this length here. And so we can even write Pythagorean theorem, right? Okay, and so that means this is 50, this is 66, and this is 83 either volt amps, vars, or watts. And there's the theta v minus theta I. Notice the same as the impedance phase. Kind of a nice coincidence. Okay, let's keep going. So we want a C such that our new power factor is 0.9 lagging. Okay, so we want this. Okay, so that means we're going to have a new current, and that means we have a new impedance here. All right. Okay, so that means we want our new desired power triangle to look like this. So instead of this steep here, the steep guy pointing up at 53 degrees, we want it down here so that S and P are closer, right? So this is like a 90% ratio, right? In fact, could we even calculate what this desired theta v minus theta I is? I think we can, right? Can we even calculate what this new Q is, right? I think we could, right? Okay, so if we know that we want a 90% or a 0.9, I think we can directly calculate that because theta v minus theta in equals plus or minus a cosine of the power factor. Because we know it's still going to be lagging, we're going to choose the positive version of this, right? Not the negative. We know it's going to be leading, then we would calculate or choose the negative if we do the a cosine. So that ends up being 25 degrees, 25.8 as opposed to 53. That's good. That makes sense. What about the Q? Well, if I know this is 50, and I know that the tangent of theta v minus theta 9 is opposite over adjacent, I can calculate the new Q. And it ends up being 50K times the tangent of 25, which is 24.2 kilovars. And this is good. Look at the new Q. The new overall Q is less than the original Q of that inductor. Okay, good. So let's say we want to calculate that capacitor now. So there's a few ways to do it. And here's the two approaches. What I can do is I can get Zn, the total Zn, where R and L are in parallel with C, set the overall theta v minus theta I to 25.84 degrees, and I can solve for C, just one equation, one unknown, because theta v would be this, okay? So I just use the phase relationship. Another way I can do it is look at it from the power perspective. So I can say that my Q new is 24.2, right? So I know this. I don't know what QC is, but I know it's got to be the difference of QN plus the original Q, which was 66. So that's easy to solve for, right? Then I know that the impedance for capacitor is just 1 over j omega c, and I know this reactive power formula. Okay, so if I know what QC is from the subtraction of these two, I have this number. And then look at that. I know omega, I know that C, I know V. I can punch that in, and again, I would get one equation and one unknown. Depending on what you like, you could go either way. They're about, maybe this is a little more work, I'm not sure. They're about equal. It just depends on how you think, but we're gonna see that both give you the same number for capacitance. So let's do the number one first, then we'll do the number two. Okay, so number one is, let's just get the overall formula for this. In the last lecture, we had just been crunching equivalent impedance. Okay, so what do we have? 1 over j omega c in parallel with the ZL, which is R plus j omega L, because that's this guy, over 1 over j omega c plus R plus j omega R. Okay, I can play the trick of multiplying by j omega c over j omega c to wipe out this one. So what do I get? R plus j omega L on the top and 1. And then I gotta be careful, j omega RC minus j, because j squared is negative, omega squared RC, no problem. So then I can clean this up, bring the real parts together, good. And then what do I have? I have the magnitude, which is essentially the polar form magnitude of the top part, which is the Pythagorean theorem, and I can see the polar form magnitude of the bottom part is just this. Notice this is the real part squared and the imaginary part squared square root. The phase is inverse tangent of omega L over R, and the inverse tangent of this is omega RC over this. So yeah, it looks a little bit hairy, but there's nothing different than the previous lecture's process, okay? So this is your magnitude, this is the phase. We really don't care about the magnitude. I just have it there just so that you can see it, because the phase is what matters. Why is the phase that matters? Because this is what we are going to set to that 25 degrees. Okay, so I go this minus this because that's how we subtract phasors or divide phasors. We subtract the phase and we set this to 25. One equation, one unknown. Notice C, omega L, R, omega R. Yeah, all those are known. The rest is just algebra at this point. Okay, there's really nothing to it. Okay, so you got theta Z equals this, right? Good. We know that's 25 and we know these numbers, right? What can I do? I can pull this guy over to the right, switch places, good. So again, like I said, this is just algebra. Take the tangent of both sides, good. I'm left with this. I have a C and a C. I can bring this 1 minus omega squared RC up. This whole thing we'll call X, and then I'm just isolating C, right? Okay, distribute the X, fine, right? And then bring it over to the other side. So I get C times omega R. If I bring this over, plus omega squared Rx, good. And then equals X, right? And then X divided by this thing is C, good. And so that means what's X? It's this guy, plug in all the numbers. And if I punch that in my calculator, which you guys can do, I get 1.13 microfarads. Yeah, this looks hard, but this is something you guys should be able to do no problem, right? This part ends up being a little bit tricky because this is like, okay, how do I combine impedance? You got to be careful about the J's and all that stuff. But I hope there's nothing on here that's horrible. Now, if you want to go down maybe an easier way, you could look at it from the perspective of power or reactive power. So let's look at this approach where we're looking at Q. Okay, so we know that the Q nu has to equal QC plus Q, right? So we say QC equals Q nu minus Q, right? And we know what this one was, and we calculate it. We want it to be 24.2 kilovars as opposed to 66. We could desire it to be 0 if we wanted to, right? So QC perfectly balances the original Q. But let's just say 0.9 power factor is fine. So that means the new QC has to be minus 42.4 kilovars. Okay. Then we take this number and just plug it into here, right? So maybe this is actually an easier way than number one. Well, if ZC is 1 over j omega C, what are these terms? Well, look at this. Bring the j up. We get minus 1 over omega C. We get 1 over omega C with a minus 90 degrees. The magnitude of ZC is 1 over omega C here. What's the imaginary part? The imaginary part is negative 1 over omega C. So we got to be careful here. It's subtle, but very important we get all the signs correct. I'm going to repeat that again. The imaginary part of ZC is negative 1 over omega C, right? And that's why I'm putting that here. And what's the magnitude? It's just 1 over omega C, no negative. But now notice we have a negative 1 here, and one of the 1 over omega C's cancel, and this is what I'm left with. Okay, this is nice because at this point it's one equation, one unknown. This is your voltage you started with. This is the negative 42. Omega is 377. Solve for C. That's it. 1.13 microfarads. It's the same value. So you might argue that number 2 is a little bit easier than number 1. Number 2 takes a little more high-level understanding of the reactive powers and how they play. Part 1 is kind of more brute force, right? A little more computation, but brute force. Either way, you get the same result, 1.13 microfarads. Okay, let's go take a look at a simulation. I spent a lot of time on the simulation, and I really hope it knocks in or locks in the intuition. Okay, so let's look at this first simulation. This is just with the inductor and the resistor. We have a 10 kilovolt RMS power supply. And look at what's going on here. The resistor is the only thing with real power. And so the real power, look at this. I took the average, so I'm getting 50 kilowatts. That's the same number we got before. And look at the inductor. I'm taking the peak, because remember, the Q is the peak of the bouncing power. It's the amplitude of the component of the instantaneous power that bounces back and forth. So for this voltage and this current, there is no the average power you can see is 0. So it's all bouncing. So that's why I can just safely take the amplitude of this number, not the average, to get Q. So you can see that it's 66.7 kilovars. Fantastic. And then I can look at the total current here, and that ends up being 8.3 amps RMS. So if I want to get the total apparent power, I'm just going to take 8.3 times 10K, which is 83.3 kilovolt amps. And that's what we saw. Good. The total power is the P of the inductor plus the resistor. So that's 50. Because the inductor has 0, it's just 50. And then the total Q is just Q of the inductor plus Q of the resistor. Because the resistor is 0Q, it's just 66. Okay, and you can kind of see what's going on. There's that lag in the current. Look at the current lagging the voltage. Okay, and you can see that voltage in green, like trying to push that flywheel of an inductor. And notice it takes some time to get that started, right? It's green and then it pushes, right? Okay, and look at the power. The instantaneous power for this guy is majority negative, but there's some blips of positive. Okay, and that means it's absorbing some power. Now, if I compare that to this one, this is the same resistor, inductor, and voltage supply, but notice the difference. I've added a capacitor. And yes, I put a little resistor here, just it's a very small resistor to make it numerically stable. But look at the current. Look at the resistance. Look at the inductance. The resistance here has the same power, 50 kilowatts. The Q has the same 66.6 kilovars is the same. And look at the capacitor, minus 42.4 kilovars. So this is balancing with this. So the overall kilovars is 24. Good. And look at this current. It's 5.56. 5.56 is much less current, whereas before it was 8.4, right? So we dropped down quite a bit. And then look at the current voltage. The current is now a little more in phase with the voltage. And look how those positive parts of the power are much decreased relative to this one. Look how much bigger the positive part is here. Okay. So I hope you can see that we're definitely getting a much better power factor, which is P over S equals 50 over 55.6 equals 0.9. And so this is your 90% power factor. And look, the overall apparent power is much less. Instead of 83 kilovolt amps, it is 55.6 kilovolt amps. So much better. So I hope this gives you a visceral, visual understanding of why we power factor correct and how it's so much better, right? And this is your 1.13 or 1.126 value, okay? All right, well, I hope you learned a lot from this simple example. And yeah, have a great day.